So, tools. Can anybody check on my YouTube channel and see if it's live? Hey, what's up?
Can I borrow that for a second?
Yeah.
Okay.
Yeah, you can clean it up too. Can anybody verify? Okay. Wait, you guys can access it? Because I didn't... Yeah, shut up. Sweet. Okay. All right. So part A is going to be the crest or the peak. What is going to be down here at part B? Correct. That is going to be the trough. Is the audio working in there on the YouTube channel? I'm using the different software, so I don't know how the levels are or anything like that. It's my first time doing the live stream at school, so. Okay. All right, and oh my gosh.
All students who are SAT testing, please report to the auxiliary desk at this time. Again, all students who are SAT testing, please report to the auxiliary desk at this time.
All right, so part C, it is talking about the portion of the wavelength that, let's see if I can change the thickness. So it's going to be traveling, hopefully you guys can see that on the stream. It's the purple part right there. Or going down and up like this. Maybe I can just make it smaller. It'll show up a little bit better. So it's either going to be this part here, so peak to peak, or from the midline all the way up and then back down to the midline. So this, come on. So this is a wavelength. So I can represent the wavelength like that, where it goes from the midline down to the trough, up to the peak, and then back down to the midline. I can go from peak to peak, like so, and that's represented by this letter C. So I can move that bad boy over here. So that's another version of the wavelength. Or the third iteration of it is I can start at the trough, go all the way up, and then back down to the trough. So that's the third way to represent the wavelength. Okay, so letter C is going to be wavelength. So if I switch over here, so this one should be crest slash peak. This one is going to be the trough. Letter C is going to be the wavelength, which means part D, that's pointing to either the positive 10 or the negative 10. So that means that this is going to be the amplitude. Because remember, the amplitude is literally the distance from the midline to either the trough or to the peak. So this would be the amplitude. And that's what D represents. Cool. All right. Let me move my little switch over. Oh, come on. All right. Now, remember the other day when we were talking about, it was kind of like a little flow chart. So we have the overarching theme of waves. So we have waves, right? It's just a way to transmit energy or information. And the two main categories of waves are differentiated between those that require a medium or some sort of material in order to propagate, and then those that do not require a medium. The ones that do require a medium are considered mechanical waves. The ones that do not require but can travel through a medium are considered electromagnetic. So the two main categories of waves are going to be mechanical and electromagnetic. So number 2 is going to be electromagnetic and mechanical. Any questions about that? Okay. So the two types of mechanical waves. So mechanical waves are ones that have to travel through a medium. If I don't have a medium, I cannot have a mechanical wave. So the two main types of mechanical waves are going to be transverse or longitudinal. Okay? So it's obviously not going to be electromagnetic or mechanical, because that would be a little weird. The two types of mechanical waves are mechanical waves. So it's going to be transverse and longitudinal. Transverse, longitudinal. And remember, these ones must require a medium in order to be present. So speaking of those two waves, what type of wave is this? The motion that's creating the wave is in the same direction as the wave. And it has compression and rarefaction. In other words, it's scrunched up or spread out. So, does anybody want to take a stab at it? Longitudinal, good. So one of the easy ways to remember the difference is, so if that's longitudinal, this would obviously be transverse. So with transverse, the direction of the wave, if I just did one pulse going up and down, it would send a pulse down the slinky horizontally. But the motion that created the wave was a vertical motion. So those two motions are perpendicular to each other, and that makes a T for transverse. Make sense? So if you if you ever have like a long extension cord and you make that big old wave that travels down, that's a transverse wave. Okie dokie. Now, this is referring to the electromagnetic spectrum. I thought I had that pulled up, but apparently not. Let me pull it up over here. Bear with me. I forgot I had it saved on my other computer. Oh, it's very tiny. I'll get something that's nice and clean for you. That's better. Sorry, bear with me, guys. Sorry about that. All right, so this is the electromagnetic spectrum. Now, remember when I mentioned before that sometimes when you search the electromagnetic spectrum in Google Images, sometimes it will be reversed. I prefer it the opposite direction, where the long waves and the short waves are reversed. So if you got the longer wavelengths over here and the shorter ones on the right, but it's the same graph or same graphic. So, if a wave has a higher energy, it will have a blank wavelength, and the options are going to be shorter or longer. So if it's a higher wavelength, or higher energy, so as I travel to the left, I'm increasing energy. So as I'm going to the left, what's happening to my wavelength? Is it getting longer or shorter? Good, shorter. So I switch over here. So higher energy, shorter wavelength. If my wave has a longer wavelength, then it will have a higher or lower energy. Longer wavelength, lower energy. Shorter wavelength, higher energy. So longer wavelength, lower energy. Cool. Okay, question number 7. Which type of wave requires a medium in order to propagate? And again, the term medium is not like a psychic. It's a material like water, air, metal, wood, stone, any type of material that the wave travels through. So which one requires a medium in order to travel? It'd be mechanical. And an easy way to think about it is, can light travel through a vacuum? Think about space. Can light travel through space? Can heat travel through space? Yes. Okay, so question number 8. If we measure a frequency of 4 hertz, what is the period of a single wave? Now remember that a frequency, the frequency of a wave is just the number of waves for every 1 second. So this is going to give us units of 1/seconds, which we can also refer to as a hertz. So the relationship between frequency and period, frequency is just 1 the period, and period is just 1 the frequency. So if I'm given that my frequency is equal to 4 hertz, and I'm asked to find the period, I know that the period is just 1 the frequency, 1 the frequency, and what I'm going to do is I'm going to insert what my frequency is, and I have 1/1 for the units, so that's just going to be a seconds in the numerator, and that matches up with what we know about the period. The period, should have put that up here, the period, move these guys down just a little bit. Should have made some space. The period is the time for 1 wavelength to pass. And we're going to have units of seconds. So we've got seconds there, so the period is going to be 1/4 of a second. Make sense? So if I have a frequency of 4 hertz, the period of a single wave. So what this frequency of 4 hertz means, that every second that goes by, so 1/1000, 2/1000, if I have 2 seconds that go by, how many waves have passed? How many wavelengths? If my frequency is 4 hertz. In 1 second, I have 4. So in 2 seconds, I would have 8. Make sense? So the frequency is dependent on the 1 second increment. How many waves that go by in 1 second. The period, on the other hand, is dependent on how long it takes for one of those wavelengths to go by. So it's typically going to be a fraction of a second, or some very, very small number. So the period of a single wave, how long does it take for one of those wavelengths to pass, it's going to be 1/4 of a second. Now, we're going to go in the opposite direction. We're going to be given the period and then asked what the frequency is. So if we know that the period of a wave, so the period is equal to 1/250 seconds, so 1/250th th of a second. That's the period. That's how long it takes for one wavelength to go by. And I'm asked to find the frequency. This is probably even easier than doing the other way, like going from frequency into period. All I have to do, because the period and the frequency are just inverses of each other, all I have to do is swap the top and the bottom. So if I do that, that means that my frequency is therefore 250 hertz. Super, super easy. And just to make sure, if my period is 1/4 of a second, if I do the same kind of move that up, move this guy down, that'd be 4/1, and that reduces to 4. And then I switch the units to hertz, so 4 hertz, and what do you know? 4 hertz. Cool. So that's the quick and easy way to do it. Oops, sorry about that. All right. So 250 hertz. Now, hopefully, you guys remember the song that I let you guys listen to, the electromagnetic spectrum song. I will add this in the comments below. It's weird saying that. Anyways, so the order of the electromagnetic spectrum is to be radio waves, microwaves, infrared, visible light, ultraviolet, X-rays, gamma rays, right? Yeah. So from lowest energy, so the ones that have the longest wavelength. So if I switch back over here. So out of these here, the category, so what we're talking about are these little categories here. So we want to put them in order of longest wavelength to shortest wavelength. So this order is going to be radio waves, microwaves, infrared, visible light, ultraviolet, they are X-rays, and then lastly, gamma rays. Now I put some extra ones in there just to make sure that you guys pay attention. All right, so just to verify, lowest energy to highest energy, cool. So lowest energy is going to be obviously radio waves, and then highest energy is gamma rays. Okay. Now the shortest wavelength to the longest wavelength. That's referring to the shortest wavelength, and I want to go towards the longest wavelength. So I just do it in the opposite order. I start off with gamma, then X-rays, then ultraviolet, then visible light, infrared, microwaves, and radio waves. And nobody told me that you couldn't see the screen. So gamma rays, X-rays, ultraviolet, visible light, infrared, microwaves, radio waves. That's from shortest wavelength to longest wavelength. The last question. So these are, you're supposed to match the category, so each one of these, with the example that's provided. So with the use of a black light, which category of the electromagnetic spectrum deals with black lights? Black lights are ultraviolet light. So we're going to choose ultraviolet, UV. And if you kind of forget, black lights typically show up as purple. Purple is over here on the electromagnetic spectrum. So it's on this side, near the shorter wavelength side. Now, I just want to reemphasize, this graphic is different than what I showed you guys before. This is flipped. So we have the shorter wavelengths on the left and the longer on the right. Okay, so don't get that mixed up. So black lights are typically purple, and that's in between ultraviolet and the visible light. So it's going to be the near UV spectrum. Okay, so this wavelength is used to see heat. So do you guys remember the example that I had with this, with the infrared camera? Good. All right, so it's a thermal camera. So this is going to be infrared. We can see this. Hopefully everybody gets this one. Visible light. We use these wavelengths to see our bones. This one's going to be X-rays. These wavelengths can be very lethal if you're exposed to them. What do you guys think about this one? So there are some that are dangerous, but I emphasize the word very because technically X-rays can be lethal if you're exposed to them over a long period of time, or a longer period of time than gamma rays, but the most lethal are going to be gamma rays. All right, so remote controls use these to change the channel. This is going to be infrared. It's like an IR remote. IR is infrared. This is how TV used to be transmitted before cable television. Radio waves, good. And Wi-Fi uses this to give you internet. What is it, Jeff? Microwaves. They also give you hot pockets. Hot pocket. See how we did? What? What did I change? Do I have this marked incorrect? Oh, yep, that was me. Hold on. Okay, I need to change that. I must have marked that wrong. Oh, because I copied this. Okay. I'll go back and change that and make that modification. I'm glad I caught that. How come nobody has told me about that with that coming up? Okay. All right. So, how do you guys feel about that? And I will modify. But you decided to let me. Yeah. Sounds like you're just slacking to me. All right. So I'm gonna stop the stream.